All right, hello again, everyone. And so this is the official beginning of the the actual lectures for the class, where I'm going to be talking about the actual material. Okay, and so this one is also still this specific part. Okay, is still a little bit introductory, but here what I want to cover is kind of the big picture of what this class is really about and what the subject is really about. Okay. I think that real analysis especially tends to be a little bit confusing for a lot of people when they first encounter it, partly because it's not, it's rarely clear and it's rarely made clear what the point of the subject really is, okay? Um, and it's a little bit complicated, it's kind of nuanced, it's subtle, what we're really trying to accomplish here. And I think that it'll help you guys sort of engage better with the material and throw yourselves into it a bit more if you have an idea of what it's really supposed to be about, okay? So here's my take on what real analysis is really about, okay? As it says in the syllabus, real analysis is sort of nominally, so let's see. Yeah, real analysis is nominally sort of the study of real numbers, which we denote by this funny looking R, and functions from R to itself. So R, this what we call blackboard bold R, represents the set of all real numbers. Or another word for it would be the number line, right? The real number line. So, you know, you probably all have a basic idea what that means. I'm going to warn you actually right off the bat that the real numbers themselves are much stranger and much more complicated than you might realize. Okay, but we'll get into that more later. So what this means, so we want to study the real numbers themselves and functions from the real numbers to the real numbers, which means basically functions which accept one variable as input, that variable being a real number, and then functions and those functions output a single real number as their value, right? So you've seen this before. You probably all have a concept of what a function is. So f of x, something like f of x equals x squared or something like that, right? Of course, this is a very simple, extremely simple concept or example of a function. We're going to be encountering a lot more complicated and strange examples of functions throughout the class. And I'm going to talk more about what a function really is, because actually in some ways this idea of a function is, this can be misleading. So this is kind of a danger, caution alert, okay? Try not to think about functions too much in these terms, okay? But ultimately, the things that we're studying do kind of resemble a function like this in some fundamental way, okay? So we're talking about real numbers and functions on real numbers. And what do we want to be able to say about these functions? The fundamental questions we're trying to answer here is, so we want to answer these questions, among others. Sorry. So for one thing, we want to answer the question, when is a function continuous? So you might have heard this term before. And it has kind of an intuitive meaning, right? Which is basically like, when can we say that a function does not jump around, the value of the function doesn't sort of jump around like crazy, erratically when you change what input value you're using, right? So if you imagine like being able to slide the input value continuously, right? if the function's value itself changes continuously with that, then we would say that the function is continuous, at least at that point, okay? But we're gonna actually make a very rigorous definition of what it means for a function to be continuous. So that's one of the major goals that we have. Another major goal would be to answer the question, what is a derivative and when does a function have one? Okay. And so you've almost certainly all encountered derivatives before. And I'm just going to warn you right away that the way we approach derivatives in this class will be a bit more intense, a little bit more serious than how you might think of them right now. Okay. It's a hairier concept than you might give it credit for, but you'll see. I'll explain this a little bit more later. Okay. And then another sort of the last fundamental question that this class tries to answer, at least that I could think of sort of right now, is what is an integral? Right, so this is all stuff from calculus. So we're sort of building the theory of calculus from the ground up and in a very rigorous way. What is an integral? And again, when does a function have one? Okay. So those are sort of the three primary questions, as I see it, that we're trying to answer with this class. Okay, that's kind of where we're heading. And I just want to say that, like, you know, as I kind of mentioned just a moment ago, you've probably seen all of these ideas before in some form. Okay, you probably have some basic idea of what it means for a function to be continuous. You have a basic idea of what a derivative is, how to calculate it, okay, and what an integral is and how to calculate those. That's what you've been taught in your calculus classes, either earlier in college or in high school or whatever, right? And in those classes, the focus is very much on computation and sort of algorithms for figuring out expressions for the derivatives and integrals and figuring out their values and stuff like that, okay? In this class, the focus is totally moved off of that, okay? We very rarely are interested in exact computations of the values of derivatives and integrals. The only times we're interested in those is when those values actually help us analyze something else or make some kind of broader statement about something, okay? In this class, what we're really focused on is basically trying to figure out how to describe the concepts of derivatives and integrals in the most general way we can, and to be able to analyze functions which are very badly behaved and strange, okay? And to apply these concepts to basically any function we possibly can. Okay, that's kind of what we're trying to do. And so we want to be able to say things like, you know, this function has a derivative, or this function has an integral between these two numbers or something like that, without really caring about what the exact value is, okay? And so part of the reason, so, you know, you might ask yourself like, well, why is that actually difficult to do, okay? And I keep hinting at this idea that basically functions, okay, here, let me sort of make a new, let me clear the board here, yeah. So clear these. Right, so why, oops, why is developing these ideas so difficult? Meaning, why do we have to spend an entire semester's worth of effort in this class just to get to the point where we can say that we know what a derivative is and that we know what an integral is, and we can figure out when those two things exist for a given function or whatever, right? Why is this so difficult? A lot of this comes down to the fact that functions can be much more complicated than you might realize. So I'm going to give you some examples of this, okay? And then I'm going to talk about why we care, okay? So, oops. So here's an example. It's called Thomae's function, okay? And you can look this up. It has like a Wikipedia page and everything. But Thomae's function is basically defined by this rule, okay? F of x for an arbitrary real input x equals either 1 over q or 0. And so the 1 over q is basically when x is rational, uh, in lowest terms, obviously. Sorry for my handwriting here, still getting used to this. And 0 if x is irrational. Okay, so you might have heard of rational and irrational numbers before. You probably have some basic idea, right? Rational numbers are basically the numbers that you can express as a ratio of two integers, right? And you can always write a rational number uniquely in lowest terms. Like 5/7 is in lowest terms, but 5/10 is not, because really that's 1/2. Okay, so basically what this function does is that if you put in a rational number, then what you do is you write it in lowest terms, and then the output value is just 1 over whatever the denominator is. So f of 5/7 would really just be 1/7, okay? And then for any irrational number, so for example, the square root of 2 or pi or whatever, it outputs 0, okay? And if you look at the graph, I'll try to sketch it a little bit. It's really hard to draw, but basically you get these kind of like hills of just dots where there are rational numbers, okay, and they kind of form these like triangles. And so it looks kind of insane, right? You just have a ton of dots here, and then most of the rest of the values are just like all down. It gets like really dense kind of down here, where there are lots of like rational numbers with tons of, or with really big denominators, right? So if I asked you the question, is f continuous and where? Obviously, it doesn't seem continuous sort of all at all places in its domain. You know, does it have a derivative? Can you integrate it? You might have no idea how to answer these questions, okay? And I don't blame you, okay? They're hard questions. That's the point of what we're trying to do. That's where we're trying to get, is to be able to answer questions like this, okay? And I will tell you, actually, f is actually continuous at irrational points, okay? So it's obviously discontinuous at, well, not obviously, but it is discontinuous at every rational number, but it's continuous at every irrational input value. So that might be surprising. F does not have a derivative anywhere, and F is actually integrable. All integrals equal 0, okay? So you might be used to thinking of integrals as like the opposite of derivatives or something. That's a very limited view of what integrals really are. In fact, in this class, we're more interested in integrals as just definite integrals. So meaning just like the area under the graph or whatever. And if you look at this graph, it's like, what would the area be? I mean, who knows? Like, just from looking at it, it seems insane, an insane question to ask. But actually, it turns out in the theory we build, it'll be easy to unambiguously answer this question and say that, yeah, you can integrate this function and all the integrals will just be 0. So that's one example, and I'll just do one more example and then we'll call it for this video. Let me just clear. So here's my second example. This thing called the topologist sine curve. So this is the function f of x, and it doesn't really matter what we do at x equals 0, but I'll just make it be 0 for x greater than 0, let's say, and 0 at x equals 0. I don't really care what it's doing anywhere else. So this one kind of looks like, you know, it starts off like this, and then it starts to oscillate really fast around here. So it ends up looking kind of like that. You can find the graph online. There's a Wikipedia page about this too. And so the, you know, the same questions apply. Like, so is f continuous? That one's a little bit more obvious. It's continuous except x equals 0. And sorry for my handwriting again. Hopefully you can read that. Continuous. Yeah, it looks kind of bad. Whatever. I'll get better. So is f continuous? Does f have a derivative? Same. But then is f integrable around 0? And the answer is actually yes. But it's not, maybe not obvious why or how you'd argue that f actually is integrable there. And really it boils down to, if you just want to think about it kind of intuitively, you know, integrating this function is kind of like taking the areas under these different, you know, sort of humps here, I guess, and adding them together, right? So as you get towards 0, there are infinitely many arches in that little region, right? So so basically you're adding up the area under an infinite number of arches, but then you just get like an infinite series, and then you just have to analyze that infinite series. And it turns out to basically just be an alternating series. So it's sort of easy to just say from that the integral is, that it actually exists. Although, well, it's a little bit more complicated because the concept of an integral is a little bit more complicated. But yeah, you'll see. Anyway, my point is just that, you know, these functions, they're out there, these complicated functions, and we need these very strong definitions to be able to deal with them. And so just to cap this off, the last question you might have would be, well, why do we care about strange functions like the Thomae's function or the topologist sine curve? I mean, what's the, you know, I've never seen that function before in my life, right? What's the point? Like, where is that useful, okay? And I don't blame you for wondering that, but here's what I'll tell you, okay, is that it might be true that some of those functions don't show up anywhere in nature, okay? Although actually I think this topologist sine curve might actually show up in some places in like physics or something, you know, really sort of deep physics, but it doesn't matter, okay? It may be, even if it's the case that these functions don't really show up anywhere else, what I will tell you is that in the process of learning how to understand these functions, these exceptionally difficult functions, people often call these kinds of functions pathological functions, okay? And so I'll probably keep using that term. So in the process of learning to analyze pathological functions and learning to develop definitions which can deal with pathological functions, you will develop a very strong understanding of functions and numbers in general, okay? It hones your quantitative instincts in a way that applies to like everything. You'll start to think about functions in the way that an analyst does, okay? And that's a very powerful way of thinking about functions. Learning to think like an analyst really is the fundamental goal, actually, of the class, okay? I mean, the theory is nice, obviously, and it's important for developing more mathematical theories, but I guess the real goal of the class, so I'll say this, the goal of the class, the ultimate goal of the class is learn to think like an analyst. And I mean a mathematical, in the mathematical sense, right? A mathematical analyst. You want to learn to think like them about functions, because analysts are very good at understanding complicated functions and doing estimation. Okay, we'll do a lot of learning how to estimate things and approximate things. Okay, that's kind of so learning how to do those things is how we get to deal with very difficult pathological functions. And so there's going to be kind of these will continue to pop up in the class, these pathological functions. So anyway, that's kind of my outline of the point of the class and where we're heading. And I hope it helps. And I'll see you guys in the next video.